take a look at what this problem is asking. This is a question about the jumping flea, and the flea reaches a takeoff speed of 1 meter per second over a distance of 0.5 millimeters. Now, 1 meter per second is about 2 miles per hour, so that's a pretty decent speed, and it reaches it over a distance of 0.5 millimeters. Well, that's less than the thickness of this pen tip, and so it gets up to a decent speed over a very, very short distance, and so therefore we'll expect a significant acceleration. I expect this number to be quite large, certainly larger than anything humans are capable of. Now, it's only getting up to 1 meter per second, and it's doing that at a very, very large acceleration, and so I expect the acceleration phase to be very, very short. Okay, so now it's the first part of the flea's jump. That's when it's actually pushing off the ground, which we're calling the jump phase. But the second phase is this. After the flea has left the ground, of course, it's going to rise up for a while, but it's only leaving the ground at 1 meter per second. And if you leave the ground at 1 meter per second, I don't really expect you to go all that high. And so I don't expect this height to be all that great. So we have two phases. We have the jump phase and we have the flying through the air phase. We expect this to be a significant acceleration in a short time, and we expect this one to be not that great a height. So we have some understanding what the problem is about, we have some understanding of what we expect the answers to be, and with that in hand, let's go ahead and get started. Now for the preparation step, I want to sketch out what the two phases of the motion look like. First off, the flea pushes off. We're going to call this the jump phase. And the flea starts with its legs like so. Its legs are tensed up, ready to jump. And then the flea pushes off, straightens its legs, and I'm exaggerating this, and ends up like so. It starts out at rest, and it ends up moving upward at a certain speed. So the flea goes from here to here. We're calling this the jump phase of the motion. Okay? Now, the flea subsequently flies through the air. And so the flea leaves the ground at a certain speed and then ends up sometime later at a certain height above the ground. Okay? This I'm going to call the air phase. Now notice this. The flea stretched its legs and took off. Then it left the ground and flies through the air. If you're going to calculate how high the flea jumps, we're going to assume that it starts with its legs already extended, and so we don't have to worry about this distance in the second phase of the motion. And so really, this problem breaks nicely into two separate pieces, the pushing off, the jump phase, and the flying through the air phase. And we know this is basically a free fall problem. So this is an acceleration phase, pushing off, accelerating upward, and then free fall with the acceleration directed downward. So we've broken the problem into two pieces, and we'll solve those two pieces in turn. Now what I want to do is this. I want to do a preparation step for the two phases of the motion separately. Then we'll do solutions for the two phases separately. And first off, let's draw a pictorial representation for this jump phase. Okay, so the flea starts with its legs tensed up, ready to jump, and it finishes with its legs extended and it's raised up off the ground. Now it starts with a speed of 0 meters per second. It finishes with a speed of 1 meter per second. And by the way, I'm just leaving off the y subscripts because otherwise this diagram is going to get far too complicated. It starts with an initial position of 0 meters. It finishes with a y position of 0.5 times 10 to the minus 3 meters. That's 0.5 millimeters. So we know where it starts, we know where it finishes, we know its initial speed, we know its final speed. We know between the initial and the final positions, the acceleration is in fact directed upward. And we're going to try to figure out what the time is, or what the acceleration is. And then subsequently, we want to figure out what is the time interval for this phase of the motion. Now, initially, we just care about the acceleration, and we don't care about the time. So let's go ahead and solve this problem by using our basic relationship for kinematics that doesn't use time. Vf squared is equal to Vi squared plus 2 times A times the change in height. We'll go ahead and use that. Now let's do a pictorial representation for the phase where the flea moves through the air, okay? And it starts like this. The flea leaves the ground, and it's leaving the ground at a certain speed, and then sometime later, it's up here in the air like so. Now, when it leaves the ground with an initial speed of 1.0 meters per second. Now notice this. This is the initial speed for this part of the problem, which was the final speed for this phase of the problem. I could also write these phases as 1 and 2 and 3 if I chose to, but for me it's just easier to treat it as two separate problems. It ends up with the final speed of 0 meters per second when it's at the top of its motion. In between here and here, we know what the acceleration is. The acceleration is 9.8 meters per second squared, and it's directed downward because this is a free fall problem. We also know the flea's initial position, and we're going to take its initial position as 0 meters. As we said, that's the starting point of the motion. The legs are already extended. If you ask somebody, how high can you jump? You don't start measuring when they're in their crouch. You start measuring when they leave the ground. And we want to know what is the final position. We want to know how high does the flea get. We want to look for what YF is equal to. So from here to here, it's a free fall problem. Time is not involved. And so again, we're going to use the basic relationship, which doesn't use time. We're going to use this one. VF squared is equal to VI squared plus 2 times A times delta Y. Now let's solve for these parts of the problem in turn, okay? And let's start with part A. What is the flea's acceleration during the jump phase? Well, we know our basic relationship is this. VF squared is equal to VI squared plus 2 times A times delta Y. Now we know everything in this equation. We know the final speed. That's 1.0 meters per second. We know the initial speed. That's 0 meters per second. We're looking for the acceleration. That's what we're trying to find. We know the change in height. It's 0 to 0.5 times 10 to the minus third. So the change in height is 0.5 times 10 to the minus third meters. So we know everything in this expression except for the acceleration, and we can solve for the acceleration. And if we do that, we get this. We get an acceleration of 1,000 meters per second squared. That's over 100 Gs. But we said we expected it to be a huge acceleration, certainly something much, much greater than humans are capable of. Now, let's go ahead and take a look at part B. The flea is moving from here to here with an acceleration of 1,000 meters per second squared. We don't expect that to take very long. Now remember, the definition of acceleration is this. The acceleration in the y direction is just equal to the change in speed divided by the time interval. If I rewrite that, I get this. The time interval is just equal to the acceleration divided by the change in speed. I'm sorry, is equal to the change in speed divided by the acceleration. And the change in speed is from 0 to 1 meter per second. So it's 1.0 meters per second. And the acceleration is 1,000 meters per second squared. Checking units, meters cancels, and I am left with one factor of seconds, which is going to come onto the top, and end up with a time of 0.0010 seconds, which is 1.0 milliseconds. So an acceleration of 1,000 meters per second squared and a very short time of 1 millisecond. Part C asks how high the flea is going to go. And for that, we're going to use this relationship right here, and we're going to rewrite it. VF squared is equal to VI squared plus 2 times A times delta Y. And for this phase of the motion, we know the acceleration. The acceleration is negative 9.8 meters per second squared. We're trying to find what is the change in height. We know the final speed. When the flea reaches the highest point in its trajectory, it's not moving. We also know the initial speed. That's 1.0 meters per second. So we know the initial speed, we know the final speed, we know the acceleration, we're trying to solve for delta y. We can rewrite the equation and we can solve for delta y, and if we do that, we get this. The change in height is 0.051 meters, which is 5.1 centimeters. Now it's time to assess, and we're going to assess the three parts of our solution in turn. Acceleration huge, as we expect. The flea gets up to a reasonable speed over a very, very short distance. So that matches our understanding of how the world works. It's a very large acceleration over a very, very short distance and a reasonably modest change in speed, and so we expect it to be a very short time. We get 1 millisecond, so that matches our understanding of how the world works. Finally, how high is the flea going to go? It's only leaving the ground at 1 meter per second. That's not a very high speed. We don't expect it to go very high. 5.1 centimeters seems eminently reasonable. If I throw my pen in the air at a meter per second, it goes a few centimeters up in the air. And so that also matches our expectation of how the world works. Fleas are capable of remarkable accelerations, but they're not going to jump that high. And that, in addition to being a good assessment of our results, is somewhat of a comfort.